Introduction. In this experiment, we are exploring how a single-stage compressor transforms mechanical work into heat. Compressors are crucial in many industries like air conditioning and power systems. Our goal is to understand the basic principles behind this energy conversion. We will be using a single-stage compressor, which squeezes air using sliding vents driven by a rotor. As the air gets compressed, its pressure and temperature go up, and then it's pushed up. Compressors work by increasing the pressure and temperature of a gas, typically air, to enable its use in various applications. Single-stage compressors in particular operate with a single compression stage, where the air is compressed in one step from the inlet pressure to the desired outlet pressure. Understanding the performance of such compressor is fundamental for industry relying on compressed air for their operations. Our main focus will be on the heating curve, which shows how the air's temperature changes over time as it compresses. The experiment involved following a set of steps to record data accurately, from setting up the equipment to analyzing the result. Theory. In a steady-state steady flow, which is SSSF process, conditions of the mass streams crossing the system control surface remain constant over time. The rate of heat transfer and work crossing the system control surface also remains steady. The energy balance for an open system indicates that the net rate of energy transfer by heat, work, and mass is equal to the rate of change in internal kinetic, potential, and other forms of energy within the system. In a standard single-stage vent compressor, as illustrated in Figure 1, a fixed volume of air is trapped between two sliding vents driven by an offset rotor. This trapped air is then moved toward to the outlet where the aerial and consequently the volume is reduced. As a result, the pressure of the air increases, causing it to be expelled through the outlet port. According to the ideal gas law, the temperature of the air will rise as the pressure increases while the volume remains constant. Therefore, there will be a temperature difference between the inlet and outlet. The compressor operates with a single inlet and single outlet. The compressor is considered a control volume because a constant mass of air flows from the inlet to the outlet within a fixed volume. Consequently, the compressor undergoes a steady state, steady flow SSFF process. To solve the energy balance for the compressor, potential and kinetic energy are regulated. This simplifies the equations used to determine the energy added to the air by the compressor, which can be derived from the energy balance equation. After the single-state compression is shut down, heat will be emitted from the compressor. This heat emission can be determined by performing an energy balance for the open system. Since there is no mass flow after the compressor is shut down, the heat emitted from the compressor will be equal to the net work done by the compressor. The derived formulas are shown below. Before use these formulas, we will convert the pressures and temperature unit into kilopascal and Kelvin respectively. Experimental setup. Single-state compressor consists of outlet pressure control valve, P2 outlet air pressure, P1 inlet air pressure, T1 inlet air temperature, T2 outlet air temperature, compressor, electric motor, spring balance, airflow meter, and the last one is inlet pressure control valve.
Methodology. First, the power was switched on. The green inlet valve was fully open. The valve was turned anti-clockwise to open it. Initial reading for all parameters listed in Table 1 were recorded at the beginning of the experiment. The tachometer was used to record the motor speed Newton. The motor was switched on. The compressor outlet pressure P2 was set to 1 bar gauge using the red outlet valve. The valve was turned clockwise to increase the pressure. The spring balance was adjusted to ensure that indicator on the motor was between the two black lines prior to recording any motor force value. The temperature of the outlet air T2 was recorded at 1 minute interval using a stopwatch until two consecutive readings were the same. To stop the experiment, 1. The compressor outlet pressure P2 was reducing to a 1 bar gauge using a red outlet valve. The valve was turned anti-clockwise to decrease the pressure. The motor and the power were switched off.
This is the data we obtained from the experiment. For the length of torque arm L is 0.2 meter. Compressor sweat volume V comp is equal to 267 centimeter cube per revolution. Specific heat capacity of air is equal to 1005 joule per kilogram Kelvin. And this is table 1 for the list of parameters for the single stage compressor unit. This is table to outlet temperature data over time at 1 minute time interval. This is table to outlet. This is figure 3, which shows the graph of outlet temperature against time. This is also known as the heating curve. This is a sample of calculation at time interval t equal to 0 second. For the specific volume through the flow meter is equal to 0.85442 meter cube per kilogram. For volumetric flow rate is equal to 0.0047 meter cube per second. For the mass flow rate is equal to 5.50081 to the power of negative 3 kilogram per second. For the power out of the motor is equal to 1266.78516 watt. So the Hc at time 0 seconds is equal to 237.72 watt. So the Q at time 0 second will be equal to 1029.07 watt. So from the sample calculations, we then could get this table 3, which shows the energy added to by the compressor and the heat emitted from the compressor. Figure 4 shows the graph of energy added to the air by compressor, Hc against time, and figure 5 shows the graph of heat emitted from the compressor against time, Qc. Moving on to discussion, we will discuss this following item, which is the heating curve and related thermodynamics phenomena, all energy conversions that happen during the compressor operation, amount of energy lost as heat compared to A, the work input to the compressor, and B, the heat added to the air. And lastly, to speculate the results, which is the heating curve if the compressor outlet pressure P2 is reduced to 0.5 bar. So for discussion 1, based on graph in figure 3, it shows that the relationship of outlet temperature T2 over time, as the time increases, the outlet temperature T2 also increases. So the gradient of the graph will decrease slowly until it reaches 0. So the graph in figure 4 above shows the relationship of energy added to air by the compressor, Hc, against time, which is as time increases, the energy added to air by compressor increase. So the magnitude of T2 minus T1 increase as the T2 increases due to the values of M and C are constant to the experiment. The graph in figure 5 shows the relationship between heat emitted from the compressor Qc and time. So the experiment starts with time 0, which means Hc is around 0, which indicates that the heat emitted from the compressor is almost equal to the power out of motor, as the heat emitted from the compressor is equal to the power out of motor minus the heat added to the air by the compressor. So based on graph Hc against time, as the Hc increase, then Qc decrease since the power of motor Wm is constant. It also indicates that the Qc decrease exponentially with time until it reaches 0. Based on the graph plotted above, figure 3 and figure 4 shows an increasing trend set of data, while figure 5 shows a decreasing trend against time. This can be concluded that the figure 3 and figure 4 are having a heat curve up, while the figure 5 has a heating down curve. So the heat gained by the molecules will increase the energy of the molecules, and the internal energy of the system will have heat loss and will decrease the energy of the system, and the transfer of energy as heat and loss to the surrounding. Discussion 2. So the energy that is being input to the system when the system heats up, when the compressor heats the air, it is allowing the temperature to increase and stabilize at one point before reaching thermal equilibrium. This is because the energy added into the system and energy lost to the surrounding is in the form of heat. Based on the figure 4, the temperature at T equal to 0 is nearly at room temperature, which means T2 is almost equal to T1. Hence, the energy added to air is equal to 0. So the outlet temperature increase as heating process occurs. Since T1 always equals to 32 Celsius, the magnitude of T2 minus T1 will increase. So the value of Hc will also increase over time. It is directly proportional to the change in temperature, giving that mass and specific capacity are constant through the experiment. Discussion 3. The amount of energy lost as heat is lower than compared to the work input to the compressor and the heat added into the air. So the heat emitted from the compressor Qc was the heat loss, while the energy added to air by compressor Hc was the energy used to compress the air. So the work input to the compressor was derived from the motor's power output, which remains constant throughout the experiment. So during the experiment, the energy input was converted into heat emitted by the compressor and energy added to air. So the result showed that a higher temperature difference corresponds to a greater amount of energy added to air and reduce energy loss. This indicates that the compressor efficiency improved at higher temperature. Discussion 4. When the compressor outlet pressure P2 is reduced to 0.5 bar, the compressor would do less work on the air, leading to a lower final temperature at the outlet. This is because the compression process will be less intense, resulting in less heat being generated. At the same time, the temperature difference between the inlet and outlet will be smaller. The smaller temperature difference will decrease the temperature gradient and reflect the decreased work input and lower heat generation. Therefore, the overall shape of the heating curve will become flatter.
In conclusion, the experiment aims to observe how heat is converted into work. The result indicate that the outlet temperature, which is T2, increases exponentially over time. Similarly, the energy added to the air by the compressor, Hc, also rises exponentially with time. Conversely, the heat emitted from the compressor, Qc, decreases exponentially over time. This suggests that as the single-stage compressor heat up, more energy is transferred to the air, while the heat loss from the compressor diminish. Over time, more energy from the heated compressor is used to supply energy to the air within the compressor. Since heat energy cannot be fully converted into work, some energy is inevitably lost from the compressor rather than being supplied to the air. Additionally, the efficiency of the single-stage compressor increases as it heats up. Given that pressure and temperature are directly proportional, when the compressor outlet pressure, which is P2, is reduced to 0.5 bar, the resulting T2 will be lower than the T2 obtained when P2 is 1.9 bar. The graph of outlet temperature versus time at P2 equals to 0.5 bar will be less steep and flatter compared to the graph in figure 3. The values of FC and QC will also decrease when P2 is reduced to 0.5 bar.
First, personal protective equipment (PPE), wear safety glasses, glove, ear protection, and steel boots. Secure loose clothing, hair, and jewelry. Second, preparation. Ensure operators are trained and authorized. Read and understand the manual and safety instruction. Third, pre-operation check. Inspect the compressor for wear, damage, and leaks. Verify secure electrical connection. Ensure the area is dry, clean, and well ventilated. Confirm the power supply matches the compressor requirement. Fourth, operation. Monitor the gauge and performance. Do not exceed the recommended operational limit. Stop if the unusual noises occur and inspect the compressor. Lastly, shutdown procedure. Do not suddenly switch off the motor as it may cause pressure surge and mechanical damage. Turn off the power supply after the experiment. Release system pressure allowing the compressor to cool down. This is the reference that we use in this experiment.